You've seen how regularization can help prevent overfitting, but how does it affect the bias and variance of a learning algorithm? In this video, I'd like to go deeper into the issue of bias and variance and talk about how it interacts with and is affected by the regularization of your learning algorithm. Suppose we're fitting a high-order polynomial like that shown here, but to prevent overfitting, we're going to use regularization like that shown here. So we have this regularization term to try to keep the values of the parameters small. And as usual, the regularization sums from j equals 1 to m rather than j equals 0 to m. Let's consider three cases. The first is a case of a very large value of the regularization parameter lambda, such as if lambda were equal to 10,000, some huge value. In this case, all of these parameters, theta 1, theta 2, theta 3, and so on, will be heavily penalized, and so we'll end up with most of these parameter values being close to 0, and the hypothesis will be roughly h of x just equal or approximately equal to theta 0, and so we end up with a hypothesis that more or less looks like that. So it's more or less a flat, constant straight line, and so this hypothesis has high bias and it badly underfits this data set. So the horizontal straight line is just not a very good model for this data set. At the other extreme is if we have a very small value of lambda, such as if lambda were equal to 0. In that case, given that we're fitting a high-order polynomial, this is our usual overfitting setting. In that case, given that we're fitting a high-order polynomial basically without regularization or with very minimal regularization, we end up with our usual high-variance overfitting setting. It's basically if lambda is equal to 0, we're just fitting it without regularization, so that overfits the hypothesis. And it's only if we have some intermediate value of lambda that is neither too large nor too small that we end up with parameters theta that give us a reasonable fit to this data. So how can we automatically choose a good value for the regularization parameter lambda? Just to reiterate, here's our model, and here is our learning algorithm's objective. For the setting where we're using regularization, let me define j train of theta to be something different, to be the optimization objective but without the regularization term. Previously, in an earlier video when we were not using regularization, I defined j train of theta to be the same as j of theta as a cost function. But when we're using regularization, when this is extra lambda term, we're going to define j train, my training set error, to be just my sum of squared errors on the training set, or my average squared error on the training set, without taking into account that regularization term. And similarly, I'm then also going to define the cross-validation set error and the test set error as before to be the average sum of squared errors on the cross-validation and the test sets. So just to summarize, my definitions of JTrain, JCV, and JTest are just the average squared error, or 1/2 of the average squared error on my training, validation, and test sets without the extra regularization term. So this is how we can automatically choose the regularization parameter lambda. What I usually do is maybe have some range of values of lambda I want to try out. So I might be considering not using regularization, or here are a few values I might try. I might be considering lambda equals 0.01, 0.02, 0.04, and so on. And I usually step these up in multiples of 2 until some maybe larger value. If I were doing this in multiples of 2, I actually end up with a 10.24 instead of 10 exactly. But this is close enough, and the third and fourth decimal places won't affect your result that much. So this gives me maybe 12 different models that I'm trying to select amongst, corresponding to 12 different values of the regularization parameter lambda. And of course, you can also go to values less than 0.01 or values larger than 10, but I've just truncated it here for convenience. Given each of these 12 models, what we can do is then the following. We can take this first model with lambda equals 0 and minimize my cost function j of theta, and this will give me some parameter vector theta. And similar to the earlier video, let me just denote this as theta superscript 1. And then I can take my second model with lambda set to 0.01 and minimize my cost function, now using lambda equals 0.01 of course, to get some different parameter vector theta, and let me denote that theta 2. And for that, I end up with theta 3, so if this is for my third model, and so on until for my final model with lambda set to 10, when or 10 or 10.24, I end up with this theta 12. Next, I can take all of these hypotheses, all of these parameters, and use my cross-validation set to evaluate them. So I can look at my first model, my second model, fit with these different values of the regularization parameter, and evaluate them on my cross-validation set and basically measure the average squared error of each of these parameter vectors theta on my cross-validation set. And I would then pick whichever one of these 12 models gives me the lowest error on the cross-validation set. And let's say, for the sake of this example, that I end up picking theta 5, the fifth order polynomial, because that has the lowest cross-validation error. Having done that, finally, what I would do if I want to report a test set error is to take the parameter theta 5 that I've selected and look at how well it does on my test set. And once again, here is as if we fit this parameter theta to my cross-validation set, which is why I'm saving aside a separate test set that I'm going to use to get a better estimate of how well my parameter vector theta will generalize to previously unseen examples. So that's model selection applied to selecting the regularization parameter lambda. The last thing I'd like to do in this video is get a better understanding of how cross-validation and training error vary as we vary the regularization parameter lambda. And so just a reminder, right, that was our original cost function j of theta, but for this purpose we're going to define training error without using the regularization parameter and cross-validation error without using the regularization parameter. And what I'd like to do is plot this J-train and plot this JCV, meaning just how well does my hypothesis do on the training set, and how well does my hypothesis do on the cross-validation set as I vary my regularization parameter lambda. So as we saw earlier, if lambda is small, then we're not using much regularization, and we run a larger risk of overfitting. Whereas if lambda is large, that is if we were on the right part of this horizontal axis, then with a large value of lambda, we run a higher risk of having a bias problem. So if you plot J-train and JCV, what you find is that for small values of lambda, you can fit the training set relatively well because you're not regularizing. So for small values of lambda, the regularization term basically goes away, and you're just minimizing pretty much the squared error. So when lambda is small, you end up with a small value for J-train. Whereas if lambda is large, then you have a high bias problem, and you might not fit your training set well, so you end up with a value up there. So J-train of theta will tend to increase when lambda increases, because a large value of lambda corresponds to high bias, where you might not even fit your training set well, whereas a small value of lambda corresponds to if you can freely fit a very high degree polynomial to your data, let's say. As for the cross-validation error, we end up with a figure like this, where over here on the right, if we have a large value of lambda, we may end up underfitting, and so this is the bias regime, whereas so the cross-validation error will be high. Let me just label that, so that's JCV of theta, because with high bias we won't be doing well on the cross-validation set. Whereas here on the left, this is the high variance regime, where if we have too small a value of lambda, then we may be overfitting the data, and so if we're overfitting the data, then the cross-validation error will also be high. And so this is what the cross-validation error and what the training error may look like on a training set as we vary the regularization parameter lambda. And so once again, it will often be some intermediate value of lambda that is sort of quote just right, or that works best in terms of having a small cross-validation error or a small test set error. And whereas the curves I've drawn here are somewhat cartoonish and somewhat idealized, so on a real data set, the curves you get may end up looking a little bit more messy and just a little bit more noisy than this. For some data sets, you will really see these broad sorts of trends, and by looking at the plot of the holdout cross-validation error, you can either manually or automatically try to select a point that minimizes the cross-validation error and select the value of lambda corresponding to low cross-validation error. When I'm trying to pick the regularization parameter lambda for a learning algorithm, often I find that plotting a figure like this one shown here helps me understand better what's going on and helps me verify that I am indeed picking a good value for the regularization parameter lambda. So hopefully that gives you more insight into regularization and its effects on the bias and variance of a learning algorithm. By now you've seen bias and variance from a lot of different perspectives. And what I'd like to do in the next video is take a lot of the insights that we've gone through and build on them to put together a diagnostic that's called learning curves, which is a tool that I often use to try to diagnose if a learning algorithm may be suffering from a bias problem or a variance problem or a little bit of both.